Good morning, ladies and gentlemen. Nice to have you here. And I'm Florian Konert, and I'm a mechanical engineer and a PhD student at BAM in Berlin, Germany. And I just prepared more overall general talk for you about the applicability of the hollow specimen technique for testing various materials in high pressure hydrogen atmosphere. And this is just because when I submitted this abstract, I didn't expect so many talks about this technique, but I was quite happy that there are so much institutes that dealing with the technique and presenting the results. So this is more general, but I just want to get some insight there and also try to link to the previous talks. So first, I just start with the motivation, then about the material and experimental conditions we performed, the materials and the results of the experiments, not so much into depth for one material, but in general, and then I will conclude. So the motivation for most of us is just clear. So we have high market ramp up of this hydrogen applications, and so there are many materials which get into application in hydrogen service, and so we have to get some knowledge how they will perform. And one approach of this is just testing the materials to overcome this challenge. And as we heard during this whole week, there are several methods, so we can just apply that. And I would just say every method has its pros and cons, so we can't just say, okay, one is the really best. But we also saw today some in situ electrochemical charging, which is quite easy to apply. And so in the first hand and quite cheap, we can do that, of course. Okay, it doesn't work, but on the left side, in situ. On the left side, in situ, but also ex situ, and we can also pre-charge specimen, especially when they are austenitic. Can do that in the autoclave, just in the middle on the right-hand side. So we just pre-charge them, take them out, and then perform our tests. Or we can do in situ cleft in the autoclave, but they are in the first hand, because of the setup, quite expensive. Let's go back to the motivation for the hollow specimen. As we heard, there are a couple of advantages because we can just combine the in situ testing with a small amount of hydrogen. So there are not so many requirements in the safety in the lab. But there are also some drawbacks yet. So it's not standardized yet, but there's really an ongoing work on that. And also the correlation of full solid specimen is not yet really clarified. Just briefly, I want to talk about the setups we used for this talk. So on the left-hand side, it's just also because it's always a big concern of the weld. So we created hollow specimen as a cross-weld specimen out of a weld of a pipeline. I will say something about additive manufactured samples out of 316L, which are also printed already in the shape of the hollow specimen. And on the bottom, you just see some tools, how you can just produce the whole of the hollow specimen. And I will just talk about the influences of just the production process of the whole. So the test setup, also shown by a couple of people already here. So we also saw some difference because we just take the approach with a hollow sample where the hole just goes through the entire specimen. So we just can purge through the specimen to get a better quality of hydrogen inside. I guess a lot of people just also saw the approach where you only have got a blind hole. There should be probably some discussion there whether what is a better solution. And just some first insights how such a hollow specimen behave if we just test it under argon on the upper of the image and on hydrogen the lower three images of the main image. So you just see in argon, you just have a clear reduction of area, a clear necking, and the 45-degree angle of the fracture or of the crack in the specimen. And in opposite, in the hydrogen charged specimen, you just have a different orientation. It's 90-degree oriented to the loading axis, and you also see that the crack just does not go really concentric from the inner center of the hole. We see this for some materials, and I guess also a lot of people just saw this at the presentation of Yannick. I guess it was yesterday, for this wire arc deposited specimen. So first of all, now I also want to say something about the way you can just interpret the results, because this is just one material, but in different microstructures. So this is a 100 Combo 6 steel, one in the annealed edition and one in the hardened edition. And it's tested under 150 bars hydrogen or 150 bars argon as a reference. And you just can see that for the softer one with a hardness of about 200 Vickers, you can see that you have a really clear ductile behavior. You have got a lot of elongation in the force displacement curve, but a clear loss in elongation when you go to hydrogen. And you also see this on the top down or bottom left picture. No, it does work. That you have a really clear reduction of area. But if you just go to the hard material, you don't have this reduction of area anymore. So this way of just interpreting the hydrogen effect would not be suitable if you have just the material behavior fully elastic, if you just have it as it is for this way. But of course, you have got a clear decrease in strength here due to the hydrogen effect. So the point I want to make here is just, okay, it depends a bit on the material behavior in general, how to just interpret the results for the tensile tests. With it, I want to come to the most, I would say, really important part and important point for manufacturing the specimen, because the state of the inner hole plays a crucial role for the hydrogen effect itself. So on the left-hand side, we have 304 synthetic stainless steel into manufacturing conditions. So the greens are just drilled, and the black ones are EDM, so electric discharge machined and then afterwards honed, just to get rid of the surface of the process. And as you can see, for the EDM and honed specimen, you have got a clear reduction in area. If you load it with hydrogen, but it's way not that big as it is for the drilled specimen. You also can see that in the elongation as well as in the reduction of area. And we tested the same for two ferritic pipeline steels, one a vintage one out of the 80s and a more modern one, and we just have the same results. Here the manufacturing conditions are slightly different. So we have got on the one hand a drilled specimen, on the other hand a drilled specimen which was afterwards weaned. So also you can see the surface roughness is just on the table top. So the weaned surface roughness is quite comparable to the EDM at home surface roughness. And the drilled, of course, are also quite similar. And as you can see, there are quite big differences in how you just produce a hole. So if you want to compare hollow specimens and results out of this hollow specimen, you want to take an eye on this. With this, I want to come to the additive affected specimen. On the one hand, as I just said, we have specimen that were printed as cylindrical bars, and then afterwards we produce our contour conventionally, and we just also have specimen which are printed near net shape. So the red ones are the printed near net shape, and the blue ones are the printed samples. But then afterwards, the contour was machined in outer geometry. And as you can see as well in the force displacement diagram, also in the spectrographic images, for the near net shape specimen, you have got a clear or a slight decrease in the elongation and fracture for hydrogen, but it's way not that big as it is for the conventionally manufactured geometry of additive manufactured specimen. But there's still hydrogen effect present in both. So as you can see for these specimen, there are also quasi cleavage areas in the fractured surface as well as for the near net shape ones. And if you take a look on the surface roughnesses, the net shape ones, of course, are way worse than the machined ones. So it's a bit of an opposite trend. If we just relate to the surface roughness, we would assume that the near net shape ones would just perform worse in hydrogen, but of course, out of the process of manufacturing of of the material itself. So the laser for the wet fusion process, you have got some surface layers or another dominating effect, which is present, but there's not yet clear whether that is time dependent or not. So we should just go a little bit more in depth into there, whether it is really effect which is present over a whole lifetime for this additive manufacturing components, if you manufacture components in this way. And with this, I also want to come now to the cross-weld specimen. So as you can see on the upper left, there's the specimen geometry in solid lines just across the whole weld metal, the heat affected zone, as well as the base metal, and as a reference only the base metal in the dashed lines. And yeah, if you just compare them for the reference specimen in the black colored lines, you just see that you have already a quite slight increase in strength, where you see more or less yielding in the force displacement curve, but you have got similar qualitative effect when it gets to hydrogen. So you have got also a clear decrease in the elongation at fracture, both for the metal for the specimen in base metal, as well as for the specimen in the cross-weld specimen. So, and just to get a closer look to the location of the fracture, we just performed these cross-cut images, and as you see on the top, you see the reference of the cross-weld specimen, and you also see in this cross-section area or cross-section image that you have a clear necking in the specimen, and also this 45-degree crack is present here, and crack is just outside the weld metal. This is just because we have a slight overmatch in the weld metal, but for hydrogen it's nearly the same. So we also have got the crack initiation outside of the weld, but we have some secondary cracks here, and also the orientation of the crack is slightly different. So yeah, these are more or less the results of the cross-weld specimen on the top. So as conclusions, I just want to say, and as you heard this week many times, in my opinion, also the hollow specimen technique provides an easy and affordable method to investigate the effect of hydrogen on the material properties in many metals, and the manufacturing process is really a crucial point you should keep an eye on. Layers due to additive manufacturing decrease the effect of hydrogen, at least for the test condition we performed here, and the reduction of area is not affected for the cross-weld specimen we saw here, which is also just related to the same microstructure where the crack happens. And the crack initiation, the weld specimen is not changed to the present of hydrogen. Yeah, and with this, I want to just thank you for your attention, and of course all my co-authors, also Alessandro Campari, who is at NTNU, and he stayed at BAM to perform these tests. And yeah, and now I'm open for questions and comments.